Huh?
I've never handed out candy before.
You haven't?
Until last night. Every 3 minutes, there was kids at my door.
That's great.
I realized how obnoxious it was.
Oh, it's so great. So,
I thought about doing that, but then I didn't want one of them to steal all the candy.
no, don't do that. We live in the avenues, and like there's some college kids and parts of it, and one of them, the kids were delighted because there were just college kids up on a balcony, and they were just throwing full-size candy bars as the kids went by, and my son's like, "This is the best!" And he was like, "I'll give you more if you play the accordion." So he played the accordion for him because he had an accordion. I thought last night when the kids there were a bunch of like 10-year-olds, a whole wad of them at my house. I don't think that there's anything as fun as an adult as trick-or-treating as a 10-year-old kid. Like, it's just like, just joy, just overwhelming, like running. Really? Was it amazing?
He's hanging out the car window. Oh my god, it's hilarious. There you go.
Just hold on. This is mom stuff. You'll be fine.
No,
Show it to me after class.
No, I got it. Sorry, I'm taking up your valuable time.
Okay, so posterior pituitary, guys. The posterior pituitary, as we saw, has a neural connection. Yes? Okay, so that's where we're going to be today. Hormones that are released from the posterior pituitary were synthesized in the hypothalamus, released because of an action potential. Yeah? Released because of an action potential. They will be released by exocytosis, just like if they were a neurotransmitter. And your textbook would call them neurohormones, remember? I don't usually use that term because it confuses them with neurotransmitters, but they're released just like a neurotransmitter would be, and they're released from the hypothalamus. Okay, so let's talk about those two hormones, the two posterior pituitary hormones. Remember, the posterior pituitary is the one that's an outgrowth of the hypothalamus embryonically. So the posterior pituitary releases two of them. They are called ADH and oxytocin. So let's talk about ADH first. ADH has a long name, and then it's got an alternate name too. So ADH, the long name for it, doesn't tell you the target, but it implies the target. Antidiuretic hormone. Okay? If you were talking about something being a diuretic or an antidiuretic, what target does it imply? Kidneys, exactly. So that is the major target. Okay, we're going to have a second target as well. So antidiuretic hormone, here's what it does in its kidney function. Okay, it's an antidiuretic. What does a diuretic do, by the way? Makes you pee. So an antidiuretic is going to do what? Hold it in, which will, of course, cause water retention and do what to your blood pressure? Raise your blood pressure. So keep that in mind for just a second. The reason that antidiuretic hormone is released usually is because the hypothalamus, which with its mass capacity to assess different inputs, is assessing the osmolarity of the blood as it goes through the brain. And by osmolarity, think ion concentration, tonicity, that kind of thing. So if, for instance, it encounters hypertonic blood, right, it would release ADH to cause the kidneys to do water retention to correct the tonicity of the blood. Does that make sense? Okay, all right. So that's one of the targets, but the other target is implied by the other name of it. The other name for ADH is vasopressin. And not only does that tell you the chemistry because it ends in IN, yeah, and the chemistry is what? IN, not iodine. Peptide, okay. But it also tells you the other target. Vaso implies what? Blood vessels. Okay, so here I'm going to teach you a rule that'll help you now and throughout the rest of the semester. If you ever have a hormone that has two different targets, you're never going to contradict what you did at the first target with what you did at the second target. They have to be consistent. So remind me what you just did to the blood pressure with the kidney target. Increased it. Now tell me what I could do to the blood vessels that would be consistent. Constrict. Exactly. Does that make sense to you? So that's the only thing that you can actually do. So the net effect of ADH is A, it increases your blood pressure by two different mechanisms, by water retention and vasoconstriction. Okay? So the good thing about that kind of mechanism is that it will, the understanding mechanism is that it keeps you from having to memorize everything, right? Because if you know what ADH does to the kidneys, then you can figure out what it does to the blood vessels. Okay? And just so you know, you are never going to know every single target of every hormone, but if you understand the basic functionality and somebody tells you a new target, you can figure out what it's probably going to do there, right? Does that make sense to you guys? Okay, vasopressin has one other functionality related to sexuality, and I'm going to come back to it in just a second. It has a whole different release mechanism and a whole different function when it's released upon orgasm, but I'll come back to it, so hold on to it for just a second. Let me tell you a clinical connection related to ADH. There is one clinical connection related to ADH. So you guys, of course, have heard of diabetes before, but the diabetes that you always talk about or hear about is diabetes mellitus, okay? Diabetes, that word, means you pee a lot. Mel means sweet, so it means you would pee a lot of sweet pea. Okay, this is a different type of diabetes, totally unrelated to sugar. This is called diabetes insipidus. You pee a lot, but it's insipid or bland or dull. Okay, now that means that somebody at one point had to taste the damn pee, right? Okay, it doesn't happen anymore, but just so you know, historically speaking, that would not be the person who went to college. So that's what you're doing here, making sure you're not the pee taster, okay? So high five to yourself. Okay, so diabetes insipidus, what it is too little ADH, right? So does it make sense to you that you would pee an awful lot if you hyposecreted ADH? Yeah? So that's called diabetes insipidus. It doesn't have anything to do with the other kind of diabetes. So you either produce or release too little ADH, or sometimes it can be a receptor sensitivity problem. Regardless, your body thinks there's too little ADH, and so you're going to pee like a racehorse. That one is far less frequent than diabetes mellitus. It's also treatable because you can inject ADH. It's a peptide, so it has to be injected. So let's just briefly talk about that. If you have something that is lipid soluble, ways to add it back to the body are myriad. You could use patches, you can take it in orally. But if it's a peptide, anybody know why you can't do oral peptide replacement? Yeah, it'd be broken down to amino acids before it was digested, so it'd just be the most expensive amino acid supplement ever, right? Does that make sense? So there's no ingesting insulin, for instance. Okay? All right, so that is a disorder. So then we're going to do oxytocin, and then we'll come back to this sexuality function with vasopressin. Okay, so let's talk about how we have known oxytocin for a while. Oxytocin is involved in parturition, which is childbirth, and it's also involved in breastfeeding. And so we know that functionality and have known it for a really long time. So oxytocin during childbirth, in addition to causing uterine contraction, it's also released in the mother and the baby, and it also causes pair bonding. Okay? And it's released again with skin-to-skin contact. If you have 20 seconds of skin-to-skin contact with anybody, you're going to release a little bit of oxytocin. And then it's released again for milk letdown during breastfeeding. Okay, so we've known about that functionality for a really long time. So what is the function of oxytocin in addition to milk letdown, in addition to uterine contraction? The bonding functionality has a really strong evolutionary significance. Because why do you want a mom to bond to the baby? So you don't kill it because they're horrible. I mean, they're great and everything, but if you look back on it, by the time they're 3, you're like, that was not fun. There was a little old wrinkly man that yelled at me all the damn time and never did a damn thing for me, ever, right? So, but you need to keep that baby alive, right? You need to feed it, and so it causes this chemical pair bonding, and it's intense chemical pair bonding, and it is evolutionarily a very, very good strategy. So it happens very strongly between the mom and the baby, and with a vaginal delivery, you release more of it, and then with breastfeeding, you release even more of it. And so there's pretty strong bonding, strong enough that, of course, we've got 7 billion people on the planet, so it must work relatively well. So what about the dad? Well, the dad doesn't have that kind of chemical bonding, certainly not to the same degree, and evolutionarily speaking, it wasn't actually as necessary for him to have that. Now, you can encourage it by doing skin-to-skin contact with dad, and then you'll get a little bit of oxytocin release, right? But anybody, even my husband's a really good dad, but he was not particularly interested in those children until they were about 6 months old and started laughing his jokes, pretty much, right? Like, that's about it. When they decided dad was hilarious, it's like, oh, this is gonna work. And I'm not saying he wasn't good, right? But a lot of times they have a different kind of response. My best friend, she could not figure out why the hell the day after she got home from the hospital, and she was like, oh my God, baby, why the hell did you send this thing home with me? Have you met me? Her husband worked for 18 hours that day. Like, that's the kind of thing that happens with like the bonding with children. It's like, oh shit, I have to keep this thing alive. I must work really, really hard. And then later on, they get the oxytocin and the bonding, but it doesn't happen immediately. It doesn't mean they're terrible parents. Okay, so that's what oxytocin does in that functionality. The other functionality of oxytocin is also really interesting, and it'll bring us back to vasopressin. Oxytocin is also released during skin-to-skin contact and massively released during orgasm. And again, oxytocin is pair bonding. It's this kind of pair bonding, and I'm sure if I tell you what oxytocin does, you can tell me which gender releases more of it upon orgasm. It's this kind of pair bonding that encourages, for instance, monogamy, at least for a while, okay? And we're not a particularly monogamous species compared to other species. I mean, I hate to tell you, I know Disney lied to you, but it's not true. But it encourages monogamy, and you can understand that when a woman, a mammal of any sort, has sex, the likelihood of pregnancy, of course, increased pretty damn dramatically, and pregnancy is very difficult to do on your own, right? Resources become problematic, and then safety becomes an issue, and those kinds of things. So what happens is you tend to bond with the people that you have sex with, right? So be careful who you have sex with, because you might not actually love them, you might just oxytocin them, right? And then it goes away, and then you're like, why the hell you eat my Cheerios? So with women, they tend to release a lot of oxytocin upon orgasm, which is an evolutionarily stable strategy. Men, however, we both release a little bit of each, but the proportions are different. Men, upon orgasm, release vasopressin, and vasopressin in that function is different. Vasopressin is not released for the same reasons, and it doesn't actually have the same effect. Vasopressin is a different type of pair bonding that is more an evolutionary stable strategy for males. So when males, of course, have sex with someone, you increase the likelihood that you're going to have a baby, right? They don't really have to stay around for the baby, but if they did, they want to make sure it's their baby, right? That they're staying around and providing resources and protection to. So here's what vasopressin does. It also doesn't fit into Disney very well. It's not a that's my sweetheart kind of thing. It's that's my bitch and this is my territory. It increases territoriality, and it increases male-male aggression. It increases aggression toward other males. And that makes sense as an evolutionary strategy, right? If you were having sex with someone and there could be a baby, whose baby do you want it to be? You want it to be your baby, right? That's who you want it. So they have done some experimentation, which I think is absolutely delightful, in which you get men together and you have them play a board game, but you dose them with a little bit more testosterone and a little bit more vasopressin. They will come to blows over that crap, man. There will be little shoes flying, you know. little houses impaled in the side of the eyeball. So anyway, and so typically what happens is upon orgasm, females release disproportionately more oxytocin and males release disproportionately more vasopressin. But each gender releases both. And I'm pretty sure I've met a woman or two who's like excessively vasopressin-y. Have you not met one? And also some dudes who are just like super, super oxytocin-y. There are a few of those. What? Do you have one? This, by the way, is oxytocin. I've told you guys this before. My husband got this oxytocin for me, which was very symbolic. It was for our 7th anniversary. It was a really good move, too, because we almost got divorced between 6 and 7. He's like, here. Here it is. And I'm like, okay, right. Okay, so that's oxytocin and vasopressin. There's a lot of research going on into those lately. By the way, people have tried to figure out whether you can dose somebody with oxytocin and make them bond to you. So, so once again, just make your own cocktails as a general rule. What? Yeah, exactly. Yeah. You can definitely bond with people. Yeah. Oh, by the way, you release oxytocin with 20 seconds of skin-to-skin contact if it's welcome skin-to-skin contact, right? You also, I like this one.
Oh, so only if it's welcome.
If it's welcome skin-to-skin contact, you release stress hormones if it's unwelcome. But guess who else you release oxytocin with? Your dog. Cuddling your dog makes both of you release oxytocin. My dog is so cute. And they haven't assessed it with cats, but I don't think it looks good, just so you know. I mean, you met him, right? Okay, all right, so let's move on to the thyroid gland. I think you might release oxytocin and your cat's just sitting there thinking about tuna. It's like, whatever. Okay, so thyroid gland. Thyroid gland is next. Where is it, by the way? Thyroid gland? Right here. Yeah. All right, so let me show you. Your thyroid is this blobby butterfly-shaped thing just under your larynx. And it secretes two different categories of hormones. And the first ones are generally referred to as thyroid hormones, and they're called T3 and T4. So the long names, we've talked about them before, but let me just reiterate something in my eyeball. Triiodothyronine and tetraiodothyronine. Each one comes from the thyroid. One has 3 iodines and it's an amine, and the other one comes from the thyroid, has 4 iodines and it's amine. For my purposes, even though your textbook really talks about the differences between them, for my purposes, you can lump them together. One of them just has a higher affinity for the receptors, okay? But I'm not going to hold you responsible for the biochemical differences or the receptor differences with them. So their big picture understanding of what those do is that they both increase the metabolic rate of almost all tissues in your body, meaning they cause catabolic and anabolic reactions to work more effectively in almost all tissues of your body. Now, this is going to be incredibly important for your overall metabolism and the efficiency at which your cells work, but there is a time in which it's absolutely crucial, and that is during brain development. You need adequate levels of thyroid hormone during brain development. So you only get one shot at brain development. So if you don't assess your thyroid hormone levels during pregnancy, you can have irreparable nervous system damage. Now, don't get me wrong, people with thyroid problems can have healthy pregnancies, but not without medical care. Okay, so also T3 and T4 are especially important during growth as well, because your metabolism has greater needs during growth. So just keep that in mind, and we'll look at a couple of disorders in a second. Okay, so as far as the chemical class of hormones, T3 and T4 are lipid-soluble amines. Iodine is required for the synthesis of both of these hormones, and iodine deficiency can cause a thyroid hormone deficiency. We don't tend to have a whole lot of those in this country because we supplement iodine in our salt, and we eat plenty of salt, right? But we'll talk about some iodine deficiencies in a little bit. So these hormones are also required for normal production of growth hormones. So just to make this make sense to you a little bit, growth is like gravy. Growth is what you do when you have done all of your basic homeostatic metabolic processes, right? So growth is extra. does it make sense to you that you shouldn't commit to growth if you don't have an adequate metabolism? So what tends to happen is thyroid problems will cause growth problems, right? If you have too little thyroid, you're going to have growth problems. Okay? Okay, so also repair problems. So let's look, before we do the disorders, let's look at the feedback mechanisms. This is the first time I'm going to show you the entire feedback loop, starting from the hypothalamus and going all the way to the thyroid. Okay, does that make sense? Okay, so let's look at this one. I'm going to simplify it a little bit further than this one does, and primarily we're going to be interested in the top part, because the bottom part is just how they talk about conversion between T3 and T4. Okay, so you guys ready? So with all of your hormones, ultimately it needs to fit into a feedback loop. Sometimes the feedback loops are easy to see and sometimes they're a little hard to picture. So what we're going to see here is we're going to look at how you regulate thyroid hormone levels. And of course the whole story is going to start with what organ? Hypothalamus, exactly. This room eats pens. Okay, hypothalamus. And hypothalamus is going to release which relevant hormone? Not TSH. TRH. Yes. And then TRH is going where? Oh, yeah. I've heard that once or twice. And the anterior pituitary is going to release what relevant hormone? And then TSH is going where? And then thyroid is going to release T3 and T4. Okay? All right, but this is not the end of the story, because now we need to talk about how your body knows when you've released enough T3 and T4, how it knows how to stop. So now the real fizz is in the feedback loop. Okay? So with the feedback loop, which will keep all of us who are healthy from having too much thyroid or too little thyroid, it goes like this. T3 and T4, remind me of the solubility of T3 and T4? They're lipid soluble, okay? Now, the hypothalamus is part of the brain. It's protected by the blood-brain barrier, right? But do lipid soluble things have to respect the blood-brain barrier? They do not, okay? So T3 and T4 can feed all the way back, negative feedback inhibition, to decrease the secretion of TRH. But in order to make the process more efficient, it can also feed back to the anterior pituitary. Okay? So what I want you to imagine is over time, in a healthy person in which this was functioning properly, if we just looked at the level of T3 and T4 over time, what would happen? Well, whenever your T3 and T4 start to go up, then they're going to start to inhibit the secretion of TRH and TSH, which will send them back down. And whenever T3 and T4 are low, you're going to have more TRH and TSH secretion, which will send them back up, right? And you're going to continue to do this so that you oscillate about a range, a proper range over time. Does that make sense? That's how it works when you're not broken. Okay? Good? Okay. And now let's break it and see what happens. Okay? So, everybody good with that? Okay. So now let's look at the clinical connections. First, let's talk about the adult one, and then we'll go back to the child one. Okay. So hypo and hyperthyroidism. Okay. So we have an adult person who is hypothyroid. What kind of symptoms would you predict in an adult person who's hypothyroid? Metabolism slower, what'd you say? They're usually gain weight. Hypothyroid. Usually gain weight. Yeah. Hypothyroid. So metabolism slower, usually gain weight, but also all of the other metabolism slower kind of things, like you're mentally and physically lethargic, very, very little energy. You're usually really susceptible to getting cold and not being able to warm up because your metabolism is really low. Does that make sense? In addition, it causes skin and hair changes. So a lot of times your hair will fall out and your skin texture will change a little bit. So there's a whole suite of symptoms that are potentially associated with hypothyroidism. And if you have X number of them, and the number changes every year, so I don't bother memorizing it, if you have X number of them, then you are diagnosed with Hashimoto's disease. Okay? Hashimoto's disease is a certain number of the symptoms of hypothyroidism. Okay? And so hypothyroidism is generally autoimmune. It means that for some reason your immune system decided to trash your thyroid, and therefore you can't produce enough thyroid. There are lots and lots of people with hypothyroid disorders. It is far more common in women than it is in men, as are all autoimmune diseases. Luckily, it's at least easy to figure out how to treat it. It's hard to get the treatment perfect, but since it's a lipid-soluble hormone, and we actually know how to make it, or a mimic of it, in the lab, you can just add it back orally. So, for instance, if a person was diagnosed with hypothyroidism, you can take something like Synthroid, and Synthroid is just a synthetic thyroid medication. And that all sounds like it's well and good, but remember that this feedback mechanism is working real time in your body, and it's really tweaky, and you can adjust it if things are low or high. Whereas with treating these hyposecretion disorders, you assess your thyroid levels, and then you predict what you think is going to be necessary, and then you take it, and you probably don't see your doctor for 2 weeks to 6 weeks, right? And if it was too much, you can cause downregulation of the receptors, and you can end up with either downregulating the receptors and becoming insensitive, or if you took too much, you could actually go from having hypothyroid symptoms to hyperthyroid symptoms. It takes a while to get this down, and then your metabolism will change, and you're going to have to reassess it again, right? Because anybody who's in their 30s in here knows that your metabolism changes, right? Like, I need to be able to eat everything. So you can supplement it. You can supplement it back. It just takes a little while to get it down. Okay, so let's talk about the next one. The next one is hyperthyroidism. And hyperthyroidism is hypersecretion of T3 and T4. And there's a suite of symptoms associated with that one as well. And what do you think they are? What kind of symptoms do you think? What? Faster metabolism? Sounds like it'd be great. Let's get into it a little further, though. Yeah, you're going to lose weight. What? You can have bone density problems because usually the other hormone comes from the thyroid is affected too. Remember, if your metabolism doesn't slow down, you also don't sleep, right? So sleep disturbances, thermoregulation problems, so you get really hot and you can't cool down because your metabolism won't settle down. In addition, there's this weird little symptom that's associated with it. For some reason, even though you lose body fat in most places, you tend to put on orbital fat pads behind your eyes, and it pushes your eyeballs out. It's called exophthalmos. And so sometimes it gets so bad that you can't even close your eyelids over it. So this is Graves' disease when this occurs. Graves' disease, again, if you have X number of the symptoms, then you get diagnosed with Graves' disease. Graves' disease is more difficult to treat, potentially. Does it make sense to you that a lot of times hypersecretion disorders are harder to treat than hyposecretion disorders? Because you have to either do surgery or have an antagonist, which those don't all exist. So if it was a tumor, then they can take it out, right? And that would remove the Graves' disease. Of course, then you're going to have to supplement it for the rest of your life because you can't do without thyroid hormone. But there is also another form of Graves' disease, and I will talk about this again a little bit later, but there is a weird form of Graves' disease that's an autoimmune hypersecretion, because let me show you how this one works. So TSH is normally what stimulates the thyroid to make T3 and T4, but it seems as if there's this weird autoimmune thing in which I got exposed to some kind of pathogen, I don't know what, and then I made an antibody, okay? And the antibody is a TSH agonist. And what does it continue to do despite the feedback loop? Yeah, it continues to cause the thyroid to release T3 and T4, even though the T3 and T4 is saying no more TRH and no more TSH. But this antibody is a TSH agonist, and it's released. So it's one of the weird situations in which An autoimmune disease actually causes you to over-secrete something instead of under-secrete something. So that's the autoimmune hypothyroidism one. We don't know what the antibody was produced in response to. They haven't actually figured that out yet. Okay.
Can you take out part of the thyroid or kill part of the thyroid, or is it all connected? Like if you
Yeah, you can lose half your thyroid. Like if you had a benign tumor on half of it, you could take that half out.
Well, if the antibody keeps telling it, but it can only produce so much, 2 to 3, if you have like half your thyroid, is that possible?
Oh, I don't know if that's ever been used as a treatment. That's interesting. Well, it releases these two, and then it releases one more hormone, which we'll talk about in just a second. It only releases 3. Okay. I've never heard that before. It's a good hypothesis. I like the way you're thinking. Okay. The other thing that is associated either with hypo or hyperthyroid disorders is a goiter. And a goiter is when your thyroid increases in size, and this is like the worst goiter ever. Okay. It's like, I mean, they don't generally look like that. It just usually looks like you have a chubby neck. So why would this be associated with either one? Well, if I had a benign tumor, it would cause a goiter, right? And then that would cause a hypersecretion. You with me? But this can also be a response to a hyposecretion. What if I can't produce enough? Then my thyroid just starts to go through cell division to compensate, right? And it gets bigger to compensate. For instance, this could be a goiter, this is a goiter in this picture, that's associated with iodine deficiency. So you don't have enough iodine, you can't make enough thyroid, so your thyroid hormone, so your thyroid like increases in size to try to compensate. It doesn't work because you still don't have enough iodine, but it tries, okay? Now, if it's an iodine deficiency hypothyroidism, it's the easiest one to treat of all of them because all you do is add iodine back to the body, right? Now, with her, with that level of goiter, it's not just going to all go away just because of iodine. She's got all the extra tissue there. But iodine deficiency hypothyroidism is not very common in this country because we add iodine to the salt, right? It's not common in countries that eat a lot of seafood because, of course, that's where you get most of your iodine. Where it has historically been more common is areas that are at really high elevation, like mountain populations. Iodine is water soluble, and so with snow melt, what happens is it all rolls downhill, and then people in the highest elevations have the lowest concentration of iodine in their water. And so if you have that in combination with inadequate access to medical care, you can get these iodine tumors. Iodine deficiency, it's actually not a tumor, iodine deficiency goiters. Okay, everybody good? Go ahead.
How do you treat that?
Just add iodine back with this one. Yeah. To add iodine, and this one would start to shrink. I mean, she would still have a lot of extra tissue, but it would go mostly away, right? It's not very hard to treat with that. Go ahead.
This might be a chemistry question, but is there iodine in sea salt?
Yes.
I know that's popular
Yeah, there is. There's natural iodine in sea salt. The stuff that we make from other sources doesn't have naturally high levels of iodine, so they usually iodize it. Yeah. Go ahead.
No, yeah, that's interesting.
Yeah. Okay. I don't wonder if our natural Utah salt here has iodine in it.
That's what I was thinking.
Because we used to be a sea, right? We used to be an ocean.
Yeah.
But I don't know if it does. The real salt that comes from out there.
I think it does.
Probably does. I mean, that's why we're so salty, right? Yeah. Yeah. Okay. One last disorder that's associated with low levels of thyroid, and that this is occurring in utero. So if mom-baby combination can't make enough thyroid hormone and it's not being treated, then you get this massively irreparable damage to the nervous system that usually results in very small because metabolism and growth, right? But it also results in mental retardation. A lot of times the babies, if it's really severe, they won't even live past infancy. And it's called congenital hypothyroidism, or the old name for it was cretinism. And what happens is these babies, their hard tissues are affected more than their soft tissues, so the soft tissues tend to grow a little faster. Their tongues, it's called hypoglossia, in which the tongue is too big for the mouth, and they tend to get hernias, like inguinal hernias and umbilical hernias, because the soft tissue is just growing faster. And then severe and irreparable mental retardation. I mean, the most important thing that probably anybody can learn about the nervous system is you get one shot to put it together. So with pregnancy, you should also always be exceptionally careful about that nervous system. And then these babies, a lot of times they don't live very long depending on the severity, but sometimes they do. These guys right here, 2 boys and a girl, and they are 17 and 20. So this is severe congenital hypothyroidism. And this was because of iodine deficiency. This would have been actually relatively easy to avoid. And they have severe mental retardation as well. Okay, so that's, they used to call it cretinism. So not very politically correct way to refer to it, but it is still referred to in the literature that way. Yeah. Mm-hmm. No, it was iodine deficiency during fetal development. Yeah. Right. So with adequate medical care, it would have been avoidable with these guys. Okay. Now let's move. Oh, we already did that. Which hypophysiotropic hormone and pituitary hormones ultimately control the secretion of T3 and T4, which is that right there. Ultimately, by the time you get finished with that, with the endocrine hormones, you should be able to make some kind of flowchart or feedback loop for each one. It'll take a little while to figure out all of them. They won't all be immediately obvious, but eventually they will all sort of, we have a section at the end in which it sort of reinforces that you can do them all. Okay, now the thyroid also secretes a separate hormone with a separate function that is not at all related to this regulatory mechanism at all. Okay, and this hormone is not, when they say thyroid hormone, they don't mean this one. This one is always referred to by its name. It's called calcitonin. It still comes from the thyroid. Its job is to lower blood calcium levels. And so what it's going to do you guys remember osteoblasts and osteoclasts? Do you remember those? Okay. So from anatomy, you learned osteoblasts and osteoclasts. And osteoblasts build bone and osteoclasts break down bone, right? And so generally in a healthy adult person, their activity is pretty even, so you don't notice any net change in bone mass, right? Okay. But what if I change the activity of either one, then I could have an increase or a decrease of bone mass, right? So what happens here is calcitonin is supposed to tone down blood calcium. And the way that it does it is by depositing it in bone. Your bone is your calcium savings bank. Does that make sense to you? Okay, and there's 2 ways you could do that with the osteoblasts and the osteoclasts. You could increase osteoblast activity, right? But it'd be even cheaper to just decrease osteoclast activity, right? So it doesn't require any more resources, right? So what these do, what this hormone does, is primarily targets the bone to lower osteoclast activity. And therefore, you're going to end up making a deposit into your bone mass. Does that make sense? Okay. So the ultimate objective that you're trying to accomplish is to regulate your blood calcium level. So if you looked at blood calcium over time, this is blood plasma calcium. What would happen is as soon as it starts to get high, you would release calcitonin and say, okay, make a deposit. And then as soon as it starts to get low, we'll release a different hormone. Why is calcium so important? Well, remember that calcium is not just components of your bone, it also is involved in neurotransmission and muscular contraction, and we will see blood clotting and cardiac muscle contraction later. Is that good? Okay, so calcitonin, the way that I remember what this one does is that it tones down blood calcium. Calcitonin tones down blood calcium. Okay, so it targets bone tissue to increase calcium storage. And you guys tell me, calcitonin would be released in response to what? Low or high blood plasma calcium levels? High, okay. And it's a peptide. And again, it is not at all related to this feedback loop. Okay. Now, I'm going to try again and see if you guys can do this reinforcement. There is one other target for calcitonin that isn't written in here. I don't really want you to memorize it, but I want you to be able to hypothesize and figure out what it does by logic. So calcitonin's job, again, is to tone down blood calcium. And we know that it does that at the bone by causing you to make deposits into the bone. What if I told you that calcitonin also targets the kidney? Can anybody figure out what it might do to the kidney? It's going to do something. So the kidney, just so you know, does not just get rid of water.
Will it excrete more calcium?
Yeah, causes you to excrete more calcium. Exactly. Does that make sense? So when you have plenty of calcium, you've already made all of the deposits you need to make, pee out some calcium. Does that make sense? Okay. And that's what I mean by it's consistent. So if it has a second target, it has to have a consistent function of that second target. Good? Okay. So the next one will be really easy then. So the parathyroid glands are next. Where are your parathyroid glands? Anybody know? They're on the back side of the thyroid. So this is an anterior view and this is a posterior view. And they look like two little pairs of nipples on either side, the back side of the thyroid gland. As a matter of fact, they used to think that they were part of the thyroid gland and they would remove them on accident, and then you ended up with a couple of problems. So these are the parathyroid glands, and they're easy because they only release one hormone, and it's called parathyroid hormone. Thank you. Yes, they're a parathyroid hormone. And parathyroid hormone targets bone and kidney to increase blood plasma calcium levels. It also does phosphate, but we'll concentrate on calcium. So what's going to happen in this story is that whenever your calcium is high, you release calcitonin, which causes you to make a deposit into bone. But whenever it's low, you release PTH, which causes you to make a withdrawal from your calcium bank in bone. Does that make sense? Okay. So PTH is released whenever it's low. So this hormone's action, you guys tell me, opposes the action of what hormone from what gland? Calcitonin from the thyroid gland. And PTH would be released in response to low or high blood plasma calcium levels. Low, exactly. And the chemical class of PTH hormone is a peptide. Okay, so one last thing. I didn't tell you this time, but now I want you to tell me. PTH also targets the kidney. Yes, causes calcium retention at the kidney. That's what it does. That's consistent, right? Okay. So just so you know, what I am likely to do on a test is to expect you to memorize the bone function and just to expect you to be able to figure out another organ function, right? If I say this is the basic functionality, in addition to this major target, it impacts this target, what do you think it's going to do, right? And then as long as I write the question clearly enough, you should be able to figure out what it's going to do if you understand the role, okay? Okay, so adrenal glands are next. And we're not going to get all the way through them. They take a little while. But I want you to start understanding the terminology so that you can fill it out. I have a log in my eyeball. Okay, so the adrenal gland is actually two separate glands. Just like with in phys, you can't just say pituitary, you always have to say anterior or posterior. With the adrenal glands, you can't just say adrenal because it's cortex or medulla, and they do two different things, okay? So the adrenal cortex and the medulla. So let me remind you where your adrenal cortex and medulla are. Where have you come here? Okay, this is the adrenal gland, cortex and medulla. This is not how big an adrenal gland is. Okay, I don't know what the hell's going on. That ain't right. There actually is some. Do you want to hear an interesting little historical tidbit about that? First off, a lot of times anatomists don't draw physiology drawings in physiology books, so you miss the connection. And then second, the history of cadaver dissection ended up with some strange conclusions about human anatomy and human anatomical variability. Because not now, but historically speaking, the cadavers that we had access to were the cadavers of the indigent, the infirm, or people who were imprisoned. And the adrenal glands are involved in your stress response. And so we kept doing all of these dissections, and they assumed that adrenal glands were just enormous in people. And then lo and behold, the sort of social stigma of cadaver donation was removed, and then we had middle class and upper class people donating their bodies, and they thought that the middle and upper class people had abnormally small adrenal glands. So they were diagnosing them post-mortem with all of these adrenal problems. But the deal was that we basically just made an improper assumption based on our original dissections, and there are like 10 or 12 of those kinds of anatomical abnormalities that we just assumed were normal because of our population group there. So it's pretty cool. Anyway, so not that you care, but that's why that damn adrenal gland is so big, because somebody didn't get the memo. Okay, so the cortex is on the outside, the medulla is on the inside. We're going to do cortex first. So as far as the terminology that goes with the adrenal cortex, you have to understand the terminology before you can get the questions. And then first, everything that comes from the adrenal cortex is a steroid, as we mentioned in the quiz question. Okay, and what does steroid mean again? Soluble cholesterol derived, exactly. So collectively, we can call them corticosteroids, and that means steroids from the adrenal cortex. Okay. Sometimes they also call them adrenocorticoids. I don't ever use that term, but I've heard it used before. The corticosteroids are divided into 3 categories based on what they regulate. They regulate salt, sugar, and sex. So now, based on the terminology, I'm going to tell you the names of the 3 different categories, and you're going to match them, okay? One category of corticosteroids are called the glucocorticoids. What do they regulate? Sugar, exactly. Another category regulates salt, and another category regulates sex. So, next name is mineral corticoids. What does that one regulate? Salt, exactly. And then we have the gonatocorticoids. Good? Yeah. And then what we will have for each one of them is at least one example. A mineralocorticoid, a glucocorticoid, or a gonatocorticoid. Is that okay? Okay. That means that when you're organizing your table, you need to collectively know that they're all corticosteroids. And then know that the ones that are regulating sugar, an example of one would be cortisol, would be a glucocorticoid, right? So that's why I'm like trying to organize the terminology for you. Okay, so let's start talking about them. The mineralocorticoids, the only one that you're going to have to learn is called aldosterone. There are more than that, but this one you're going to run into 2 other body systems, and you're also going to run into it in your future. So what this one does is it controls ion levels, mineral salts levels. So this is aldosterone. And aldosterone, try to learn it this time because you're going to run into it in the endocrine system. You're going to run into it again in the cardiovascular system, and then again in the urinary system. So if you can get it out of the way, the rest of your semester will be a bit more pleasant. So I'm going to simplify what it does for you, okay? Its main target is the kidney, okay? And here's what it does. You guys know that the kidney allows for exchange between the blood and the urine, right? Okay? So I'm going to say this is the blood, and this is the urine. We'll draw the anatomy more carefully when we get to the kidney. Here is what aldosterone does to simplify. Aldosterone retains sodium at the kidney, always at the expense of another positive ion. And the 2 other positive ions are potassium and H+. So you can see that you could use, for instance, and I'm not going to ask you in detail about this until later, you could see that you could use aldosterone to regulate sodium, to regulate potassium, to regulate pH. Good? Okay. In addition, if you retain sodium, what does it typically do to your blood pressure indirectly? Yeah, it tends to raise your blood pressure. Okay, so keep that in mind. That's why we're going to run into it in the water retention. That's why we're going to run into it in the cardiovascular system because of its impact on blood pressure. And obviously we'll run into it in the urinary system because of what it's doing, right? It's working at the kidney. Is that okay? Okay, so by the way, that drawing is just a visual representation of the same thing that's written right there. It's just a little easier to remember. Okay, everybody all right with aldosterone? Okay. Now, you won't understand the significance of why it does that until later, but we've got more time for that later. Okay, so the next ones are the glucocorticoids, and the glucocorticoids these are the most complicated hormones that I've ever encountered. I will simplify them for you as best I can. But realize I have to fib to you a little bit and oversimplify it because you could really do a PhD on this hormone. The most common glucocorticoids are cortisol and corticosteroid. They always start with corta. Okay, and so let me try to give you a big picture understanding of what these do before we get lost in the details. Okay, so the major impact of these hormones are to keep you alive during times when you can't or won't eat. Okay, so I want you to think about being really, really sick and sleeping for 15 hours, right? Or trying to get through the first trimester of pregnancy when you cannot freaking eat anything and you're wondering how the hell you're staying alive, right? Some people can't even drink water. Like you drink water and you just throw it all up. So, but we know that your brain continues to need glucose, correct? And you continue to need at least a baseline metabolic rate to keep you alive, right? You need to feed yourself. So what does cortisol do? Cortisol makes sure that you have adequate circulating nutrient levels to keep you alive, and it depresses the metabolism of everything non-essential. That makes sense? So every single night, just so you know, you release cortisol to get you through the night. And what it does is it depresses the metabolism of everything non-essential and then dumps stored nutrients into the bloodstream to keep you going baseline and to keep your brain adequately supplied. That makes sense? So for instance, does it make sense to you that it might release glycogen stores from the liver, right? And then make other things like burn fatty acids, right? Does that make sense? So of course, once we get into cortisol deeply, we will talk again about gluconeogenesis and glycogenolysis and all of that kind of business. But do you understand the big picture? The big picture of what cortisol does? Corticosterone does similar things. Okay, so the metabolic effects are to raise your blood glucose and other nutrient levels. And so it does this by, let's look, make sure these terms make sense to you. Glycogenolysis, yes, breaking down stored glycogen. Lipolysis, because some things can burn fatty acids, right? Okay. If necessary, gluconeogenesis in the liver. And so this is considered not an anabolic steroid, but a catabolic steroid. Yeah? Okay. Now, it sounds like it would be bad if it's a catabolic steroid, but it is the one hormone that you absolutely cannot live without. Because there are always periods in which you are not taking in nutrients, and you always have to be able to make sure that you're supplying your basic metabolism. So you can't live without this nutrient at all. It also has some other functionality, and I'll just talk about this and then I'll let you guys go before we go to the gonatocorticoids because the other class is a couple minutes behind. Okay, so in addition, it also has some other functionality. So just remember, big picture, that what it does is dumps nutrients into the bloodstream, but depresses the functionality of anything non-essential. And just so you know, it is a pessimistic hormone. It doesn't really know if there's going to be tomorrow. So even things that you might consider essential, it doesn't consider essential, like long-term immune function. If I'm not going to make it through the night, do I really care about T-cell development? No. And how about reproductive function? What do you think it's going to do to that? It's going to depress reproductive function. What about healing, right? I just need to get through the night. We'll deal with healing after we make sure that we are actually going to survive. So if you repeatedly secrete this stuff, you're going to end up with some problems. So it does suppress your immune system. It's a massive anti-inflammatory. Inflammation is the first step of healing. So it can be used therapeutically. So you guys have heard of prednisone, right? What those are is cortisol or corticosterone agonists. They mimic the effect of cortisol or corticosterone, and what they do is they massively suppress your inflammatory response, but they do that at the expense of like your metabolic effects. You tend to have metabolic disturbances, and they actually, if you use them for a long period of time, they're going to suppress other immune functionality as well. So it's the most effective anti-inflammatory that we have, but it's not without its side effects. So it suppresses your immune function. It also has some impacts on your vessel function. So what your vessels should do is they need to be really responsive when you tell them to vasoconstrict. And cortisol helps them to be responsive when you tell them to vasoconstrict. And then it's also got a massive function in adapting the body for stress. So cortisol is supposed to help you get through these sort of short-term or even chronic stresses. So like disease, cortisol will help me get through the stress of disease or the stress of starvation, right? So it's massively important in adapting the body for stress. It is also necessary for the synthesis of growth hormone. So if you can't support yourself while you're sleeping, you're not going to commit to growing. And it's absolutely necessary for life, especially like during prolonged fasting periods. It must be supplemented if it's hypersecreted or hyposecreted. So we will come back to this because this is going to be involved in the stress story that we tell at the end of this set of notes. Because when you chronically secrete cortisol, when you have a really, really stressed out life, like somebody hits you upside the head every day and you don't have enough food, or somebody's about to bomb your damn house, you secrete cortisol very, very consistently over long periods of time, and it ends up trashing your body in ways that are very predictable. We'll talk about that at the end of this set of notes as we talk about the stress response. So I will stop there for today.
So for military, are corticosteroids and cortisol, they have the same functionality?
Yeah, they actually interact at slightly different receptors, but yes, you can group them, right? If you get later into your career, they may tell you the individual functionality, because some of them have receptors on some places and not on others. So, oh no, I'm just gonna go like take care of it. Thank you.